Okay, what we want to talk about right now is we want to talk about Dalton's law of partial pressure. And Dalton's law of partial pressure, here's what I want you to imagine. We've got a container, and that container has a particular volume. So we have a volume, and we also have a particular temperature. And in that container, we've got some nitrogen and we've got some oxygen. And let's just say we've got a certain amount of CO2 as well. Well, Dalton's law of partial pressure says that each one of these gases that's in this container is going to be banging on the inside of the container, creating pressure. And so each one of them, you could think of each one of these gases that's behaving in an ideal manner as having its own unique pressure component that it's exerting inside this container. And I could exclude all the other gases and just think of that one gas, let's say oxygen, exerting its own individual unique pressure as a contribution to the total pressure. And so that's essentially what Dalton's law of partial pressure is saying. The total pressure of a mixture of gases equals the sum of the pressures that each would exert as if it were in the container by itself. And we can express it mathematically as the total pressure. So this is pressure total. In this case, is equal to the sum of the pressure contribution, the partial pressure contribution of nitrogen plus the partial pressure contribution of oxygen plus the partial pressure contribution of CO2. And so that is Dalton's law of partial pressure. Now, here's what I want you to consider. Well, why is, let's say, oxygen producing that particular unique contribution of partial pressure? And what we want to do is we want to think about this with respect to the ideal gas law, and that's PV equals N, that's moles, times R times T. And I think you can agree that if we think of the total number of moles, so let's just say I add up all the moles of all the gases that are in this particular container, and I do a calculation for the total pressure, there is a direct relationship between the total number of moles and the total pressure of all of the gases that are in the container. And we can further extend that to look at this. Well, wait a minute. All these gases have the same volume and the same temperature that they inhabit. So I could literally cross out temperature because temperature is the same for every single one of those gases, and so is the volume. R is just the gas constant. It's a constant. It doesn't change. And so that's going to give us this relationship where pressure is directly proportional to the number of moles of each one of those gases. So this is and so we can relate that to, let's say, the partial pressure of nitrogen is directly proportional to the number of moles of nitrogen that's in that container. Put more moles of nitrogen into the container, you're going to have a higher partial pressure because these are directly related to each other. So let's go ahead and demonstrate that with a nice little problem. First, let's talk about the mole fraction. So mole fraction is nothing more than the ratio of the number of moles of one of the components to the total number of moles in a particular mixture. And we'll total out the total number of moles in a mixture as being unity. And then the partial, and then we'll have some fraction of the number of moles that are in that, that total number of moles. So we can express it like this. Now, mole fraction actually has a symbol, it's big, goofy looking italic X. That's not a very good version of it. But what this means is this is moles of one component, okay, one component of a mixture, one of a mixture. And down here, what we have is we have the total number of moles. This is just total moles in the mixture. Okay, so you add up the moles of every component of the mixture, you get the total number of moles. This is always going to be a decimal. It doesn't have any units because remember, this is just a fraction of the total. So it'll always be less than 1, some sort of a decimal. That would be like saying, well, let's say I have 10 moles total, and out of the 10 moles total, I have 5 moles of one of those things, and that's just going to be equal to 0.5 or 5/10. It's always going to be a decimal like that. Well, considering the argument that we just made, that we have this direct relationship between the partial pressure of a gas and the number of moles of that gas, we can come up with a ratio. So let's say we're talking about the partial pressure of nitrogen divided by the total pressure, and that's going to equal the number of moles of nitrogen divided by the total number of moles of all the gases that are in the container. This is the mole fraction. Okay, and I'll just call it frac if that's okay. Little Battlestar Galactica reference. All right, so that's the mole fraction. And this, in essence, is the fraction that's of the partial pressure of that gas, in this case nitrogen, of the total pressure. And so I will call this the pressure fraction. I don't think anybody else calls it that, and I don't know why my pen's not working, but that's okay. So that's pressure fraction, and I'll just stick with frac right there. See if I can improve. Oh, that's a little better. Pressure fraction. And so what we can say is the pressure fraction, pressure frac, is equal to the mole frac. I know I make funny F's. All right, so pressure fraction is equal to the mole fraction. So this is awfully useful for you in solving problems of a particular type. Let's say I know the number of moles of one of those gases, I know the total number of moles, I know the total pressure, and I want to know the partial pressure. Well, I can solve for the partial pressure by simply multiplying both sides by the total pressure. I could also solve for the total number of moles if I knew the partial pressure and the total pressure, or I could solve for the number of moles of nitrogen in this particular case if I knew the total number of moles and I knew the pressure fraction. So as long as I have 3 out of the 4 variables, or I can derive 3 out of the 4 variables, I can derive the 4th variable. And so that's going to give us this relationship. Pressure fraction, well, that didn't work out the way I expected it to, is equal to the mole fraction. And so I can solve for the partial pressure. Why did that get tiny? I don't know, but there it is. And so I can solve for the partial pressure of one of those gases, taking the mole fraction times the total pressure. All right, so let's go ahead and solve a real problem that's in your PowerPoint notes. Somehow I didn't make a video on it, and I'm getting a little long-winded here, so let's make some short work of it. So here we go. The total pressure on the surface of Titan. So Titan is a moon of Jupiter. Pretty cool. Not Jupiter, Saturn. That's the mistake everybody makes. It's actually a moon of Saturn. And it has a total pressure of 1,220 millimeters of mercury. We don't need to convert to atmospheres because we're not using the ideal gas law. Okay, so we can use any units of pressure that we wanted. The atmosphere consists of 82 mole percent nitrogen, 12 mole percent argon, 6 mole percent methane. So what this means is percent. Percent always means out of, so percent means out of 100. So that means that this is going to be the total number of moles since it's a mole percent. And we're going to use that pressure fraction, partial pressure in this case of N2 divided by the total pressure is equal to the number of moles of N2 divided by the total number of moles. And the total number of moles is going to be 100 because it's in percent, mole percent. So here we go. So the partial pressure of nitrogen is going to be equal to the mole fraction of nitrogen, which is 82 divided by 100, that's NT, the total number of moles, times the total pressure, 1,220 millimeters of mercury, which is going to give us 1,000.4 millimeters of mercury. We're going to do the same thing for argon. Partial pressure of argon is equal to 12 moles of argon out of every 100 moles times 1,220, which is going to give us 146.4 millimeters of mercury, I believe. And then finally, the partial pressure of methane. This stuff right here, 6 moles out of every 100, because it's 6 mole percent times 1220 is equal to 73.2 millimeters of mercury. All right, so here's the test. Dalton's law of partial pressure says that the total pressure is equal to the sum of the partial pressures. So if I add all of these, this is the partial pressure of nitrogen plus the partial pressure of argon plus the partial pressure of methane, I will get the total pressure 1,220 millimeters of mercury. And that's a clear demonstration that this pressure fraction is equal to the mole fraction idea is something that you can use to solve problems. Okay?